This lesson is writing polynomials from roots. So think about when we've found the roots these past couple lessons. Now we're going to go backwards. They're going to give us the roots, and our job is to write the polynomial from them. However, here's an example to start us off. And it says find the roots of this polynomial here. And we find the factor of the constant, leading coefficient, and that gives us all of our possible zeros. We have 8 numbers to try, so we look at the graph and we see that it'll be here and here. So that tells us we can try -1 and 2. So we do synthetic division to kind of verify that those work. And when I plug in -1, I get 0. So then I plug in the next one, 2, and I get 0 also, which means those work. I'm left with 2 plus 0x plus 2x squared. So I use that right here to do the quadratic formula. Or sorry, they just solve. So you subtract 2, divide by 2, and do the square root to give you an answer of x equals plus or minus 1, or I. What we notice here though is my zeros are these two numbers. Then I have a positive I and a negative I. So the point I'm trying to make with this example is, at this point we should start to see that the radical zeros, including the imaginary ones, square root of -1, always come from a plus or minus in front of the radical. So we always have a plus or minus here whenever we do that last step of quadratic formula. And here are the theorems that make that true. Complex conjugates theorem. If it's a polynomial and you have a plus bi as a 0, then you also have a minus bi as a 0. Same with the rational conjugates. If you have a plus the square root of b, then you will also have a minus the square root of b. So let's look at a couple examples here that explain that. We can find the conjugate of each one. Sometimes you are given the zeros of a polynomial and asked to write the polynomial of least degree with integral coefficients in standard form. That includes all the given zeros together. That includes all the 7 given zeros. Together, these two theorems tell us that if you are given a list of zeros that include a plus bi or a plus square root of b, you must also include the conjugate. So for example, the conjugate of 7 minus square root of 2 is 7. That's too big. Is 7 plus square root of 2. The conjugate of a -3 radical 5 is a positive 3 radical 5. The conjugate of 3 plus 2i is 3 minus 2i. And the conjugate of 11i is a negative 11i. So if we're given something or missing a piece, that's where the piece is going to come from. So, first example says, write a polynomial function f of the least degree that has integral coefficients and zeros of 4, -1, and square root of 5. So this is where it's going to come into play of using the theorems above. If I have 0 plus square root of 5, which is what I'm given, then the other one, and that 0 isn't really needed, would be negative radical 5. And here are the steps on the right of how to set these up. So set up each 0 with x minus p. So x minus p, that means we're going to plug in these terms here into these parentheses. So x minus 4, x minus a -1, x minus radical 5, and x minus a negative radical 5. And I can simplify those down to say x minus 4, x plus 1, x minus radical 5, and x plus radical 5. Step 2. Multiply the radical factors. So if you have square root of b times square root of b, that's square root of b squared, which is just b. So a minus c square root of b times a plus c squared of b is just a squared minus c squared b. So what it's saying here is, I'm going to look at these two terms right here. I can do the distributing method, and that would give me x minus 4 here, x plus 1 here, then x squared minus radical 5x plus radical 5x minus radical 5 squared. This can simplify because we know a negative radical 5x and a positive radical 5x, those two are just going to cancel. And then I can simplify this piece here. So I get x minus 4, x plus 1, x squared, these will cancel, and negative radical 5 squared will just give me minus 5. Then multiply or distribute the remaining factors 2 at a time in any order. So pick any two and just start multiplying. I'm going to go with these two first. Let's not forget that I should be writing f of x equals for all of these. So when I multiply x minus 4 and x plus 1, I end up getting x squared minus 3x minus 4. Bring this one down. Then you multiply those two. And that would give me, if I'm going to go one piece at a time, so I'm going to go this to these three. That gives me x to the 4th minus 3x to the 3rd minus 4x squared. Then I go this one to those three. Minus 5x squared plus 15x plus 20. Combine like terms, so it's the last one. State your final answer as a polynomial function in standard form. So combine like terms and put it in standard form. Your final answer is f of x equals x to the 4th minus 3x to the 3rd minus 9x squared plus 15x plus 20. And this is your final answer. So a little thing here, multiplying with radicals. Here's a different example. If you have x minus 3 radical 2 and x plus 3 radical 2, you get those, and we know that these two here will cancel, and that's what you get. Now let's do an example with an imaginary number. Write a polynomial function f of least degree that has an integral coefficients and zeros of 7 and 6i, which means if I have 6i as a 0, then my other 0 will be a negative 6i. So I want to, once again, first step, set it up with the zeros. That is x minus 7, x minus 6i, and x minus a negative 6i. That reduces to x minus 6i and x plus 6i. Next step, multiply the imaginary factors. I squared equals a negative 1. So a minus bi times a plus bi equals a squared plus b squared. So when I see this here, I'm going to multiply those first. That's x squared plus 6ix minus 6ix minus 6 squared I squared. When I simplify, I get x squared, these will cancel. Then I get a negative 6 squared is 36, I squared is a negative 1, so that gives me x minus 7 and x squared plus 36. Multiply, distribute the remaining factors in any order, and then state your answer as a standard form, the polynomial standard form. So I get f of x equals x cubed plus 36x minus 7x squared minus 252. That is not in standard form. So I get this. And the last example. Write a polynomial function f of least degree that has integral coefficients and zeros, -3, 3/4, and -1/2. Notice, since they do not have a radical or an I, there are no pieces missing. It's only those three. Only these two will have a plus or minus of each one. So, first step is to write them in. And we'll get to this part over here after. So I'm going to write them in first, and I get x minus -3, x minus 3/4, and x minus -1/2. So it says, if you want only integer coefficients, meaning you don't want to deal with fractions, I don't want to deal with them, then it must become q x minus p over q. So all it's saying is whatever's on your denominator, put that in front of that piece, and then you're going to distribute that in to give you q of x minus p. Use x minus the given 0, then multiply by the denominator, distribute into parentheses to change everything to integers. So what I would do here, I have f of x equals x plus 3. Then I have x minus 3/4 and x plus 1/2. So I'm looking at my coefficient, my denominators now. This is the 4 and this is a 2. I'm going to put a 4 in the front of this one and a 2 in the front of this one. When I distribute those in, I end up getting f of x equals x plus 3, 4x minus 3, because that 4 will cancel with this 4, and 2x plus 1, because that 2 would cancel with this 2. Then, just as we've done before, pick any two and multiply them together. I'm going to do the first two. F of x equals 4x squared plus 9x minus 9 times 2x plus 1. Multiply those two pieces together and you get f of x equals 8x cubed plus 22x squared minus 9x minus 9. That is your final answer.